Welcome to Lecture 4. We will continue our study on analog to digital converters with Part 2. Successive approximation register analog to digital converter. With the exception of the flash converters, which will be studied in the next chapter, successive approximation converters, or SARs, are fastest and the most popular ones. Figure below illustrates 4-bit version of this converter, which utilizes the digital to analog converter. This converter produces a signal which depends on the counter content. Now DAC's output is compared to the input analog signal to see if it's higher or lower than current voltage produced by DAC. The basic idea is to determine the value of the number within a certain range by several successive estimations. Each estimation would be evaluated and it would be known if the estimate was equal or less than or too greater than number to be determined. So take a look at the block diagram of typical SARs, digital to analog converter. Counter or microcontroller circuit sets the digital patterns of the values, which we call hunting, depending on comparator's answers. That's the basic function of the counter circuit. This counter circuit feeds output register. When acquisition or hunting is finished, the output register latches converted word until next conversion. DAC immediately produces analog voltage at the output, which corresponds to digital word from counter circuit. And eventually we have a comparator, U2 here, that makes decision whether the content of a DAC is higher, then the output will be 0, or lower than the current amplitude of the analog signal. Let us take a closer look into the operation of successive approximation register analog to digital converter through the following rather simple example of a converter with only 4-bit resolution. However, the same principle and procedure can be equally applied to any arbitrary resolution. Say that we want to execute the acquisition of an analog input sample with amplitude of 13 volts. The least significant bit of the converter is by definition full-scale range over total number of increments. For simplicity, assume that the maximum output voltage of DAC is 15 volts and the minimum is 0 volts, so that the full-scale range is exactly 15. The total number of increments is 2 to the power n-1, where n is equal to 4 bits, making total number of increments equal to 15. Consequently, the least significant bit is 1 volt per count. Since SAR has no idea what is the amplitude of the current sample, it will expect from comparator to give a rough estimation on whether the current sample is higher or lower than the half of the maximum value, which is 15 volts decimal or 1111 binary. Therefore, in the very first step, or first clock, the control circuit sets a SAR value to 1000 binary, or decimal 8. That is a half of the total range. To find the actual voltage that DAC will produce for this input value of 1000, we have to multiply least significant bit with decimal value, or call it a count, and that would be 1 volt per count times 8 counts equals 8 volts. You should appreciate now how simplified this example is, because the count tells us right away what is the voltage. In reality, the least significant bit might have a value of, let's say, 0.0625 millivolts per count, which would require substantial calculation to find the voltage. Now the comparator has to make a decision if this amplitude of a sample higher or equal than 8 volts, or is it not? meaning is it lower than 8 volts. In our case, V plus potential at the non-inverting terminal is equal to 13 volts, that's the analog sample, and V negative potential at the inverting terminal is equal to 8, making the difference of 13 minus 8 equals 5 volts. 5 volts is higher than 0, and the output of the comparator goes to positive saturation, which corresponds to a logic high, or 1. And the answer would be yes. That means our sample amplitude is higher than offered a half of the range, which is 8 volts. After the first clock, control circuit can make a conclusion that the analog amplitude is higher than half of the range, so it must be somewhere in the upper half values. In hunting terminology, we would say that the SAR undershoots target value, and we have to add more voltage to DAC output. Therefore, the control circuit makes decision to keep current bit, which is most significant bit, at 1 and add half of upper half of values, which loading SARs with the 1100 binary or 12 decimal. Now the DAC provides voltage of 1 volt per count times 12 counts equals 12 volts. The comparator compares now the difference of 13 volts minus 12 volts is the DAC voltage, which gives us 1 volt positive. This drives the output again into positive saturation, logic high, or 1. So the answer whether the current sampling is equal or higher than 12 volts would be yes, logic 1. Again, the control circuit makes the conclusion that SAR is undershooting and has to add more voltage to DAC. Now, in third step, or third clock of the operation, the control circuit increases SAR count by half of the half, that means a quarter, of upper half of the total range values, which would be 1110 binary or 14 decimal. This count DAC converts into 1 volt, which is least significant bit, by 14 counts give us a 14 volts. However, the comparator now sees that the differential voltage of 13 volts at the positive terminal minus 14 volts at the negative terminal or inverting terminal will give us negative 1 volt. The negative differential voltage drives the output into negative saturation, which corresponds to logic low or 0. 0 level from comparator tells control circuit that now it overshoots target value. In other words, the DAC voltage is too large and has to be reduced. That would be the reason that in last step, which is the fourth step of the clock, or clock fourth of the operation, control circuit sets current bit back to 0, 1100, and then increases lower bit position, which happens to be the least significant bit from 0 to 1. SAR is now loaded with the count value of 1101 or decimal 13, with the DAC voltage change from 1 volt per division times 13 counts to 13 volts. Of course, whether the analog sample is equal or higher than 13 volts, the comparator should answer with yes, that means 1, and this concludes the full conversion. We counted 4 steps for 4-bit converter with 16 different amplitude levels. In case of a 256 levels, for instance, 8 clocks would be sufficient to complete the conversion, which makes SAR analog to digital converter relatively fast. There is an interesting video clip which visually illustrates operation of successive approximation register analog to digital converter. It was by far one of the most complex multisim simulations I have designed or came across. To avoid excessive complication in analyzing detailed schematics and its operation, most of the circuitry has been replaced by blocks so that the presented schematic would resemble block diagram of the typical SAR converter. Instruments are connected to monitor current clock execution, DAC voltage, and reset pulse upon completion of the conversion. I have also included a convenient switch, as you can see here, S1, called mode, which provides either single conversion or continuous conversion. As you would verify yourself in lab experiment 3, a real SAR analog to digital chip also has almost identical functionality. However, this simulation does not include sample and hold circuitry. Instead, a variable analog signal is simulated using potentiometer driven by DC voltage, VCC 5 volts, as to keep the constant amplitude while conversion takes place. The importance of this video clip extends beyond visualization of a SAR operation. It is also a powerful teaching tool because exact readings of the instruments help students to verify their own calculations. For each value of the selected input amplitude, students should create hunting table as shown in previous slide and verify a result by looking into the DAC voltage and into the binary, actually hex display. The only difference is that this video covers 5-bit resolution SAR and that the least significant bit is set up to be around 160 millivolts, as set by EREF voltage to cover full-scale range of approximately 5 volts. It is set up in such a way to cover maximum amplitude of the analog input. Students are encouraged to test yourself against this simulation. Unfortunately, actual multisim file is not available to students, mainly due to extensive abuse of the circuitry, which usually renders simulation to crash and or not to work. Let's just say a couple of words about the advantages and disadvantages of the successive approximation analog digital converter. Ideally, successive approximation conversion takes only n steps or n clocks, where n is the resolution or number of bits, so it is very fast converter. Disadvantage would be that the accuracy of the SAR converter depends on accuracy of the DAC used in process. A switched capacitor technology is often used in modern SAR converters. For good accuracy, the reference voltage must be very precise. In addition, the sample amplitude must stay constant during the whole cycle, so a sample and hold circuit must be used. And at the end, let us say a couple of words about a flash analog to digital converter. The type of analog digital converter which can perform the fastest conversion is called flash or parallel converter, illustrated in the figure shown, as only a 3-bit version. A reference voltage is connected to voltage divider that divides it into 2 to the power n minus 1, which is 7 equal increments. N is number 3, total number of bits. Each level is compared to the analog input simultaneously by corresponding voltage comparator. So as you can see, analog input is connected to each of those comparators. And voltage divider, this huge voltage divider, will set up a reference voltages for comparison for the first, second, third, fourth, fifth, sixth, and in this case, seventh comparator. For any given analog input, one comparator and all those below it will have a high output. All comparators are connected to a priority encoder, which produces a binary output corresponding to the input having the highest priority. So if priority encoder is something new for you, let me tell you, simply that's a digital circuitry which actually codes the highest bit that is set to 1 at the input and identifies its position with the digital outputs. So let's say if all are 0, priority encoder will set D0, D1, and D3 to 0. And if the, let's say, second one is set up to 0, then the least significant bit will also be set up to 1. So you will have 0, 0, 0, 0, 0, 1, 1, which will be coded as 2, which means that D0 will be 0, D1 will be set to 1, and D2 will be set to 0. So you will have 0, 1, 0. Digital outputs indicates bit position of the highest bit that is set to 1. That's the function of priority encoder. The principal disadvantage of the flash converter is the need for a large number of comparators, 2 to the power n minus 1. For let's say if we are talking about 8-bit flash analog to digital converter, it will require 255 comparators. Some modified design techniques, though, reduces this number to 30 comparators, but sacrifice the conversion time in return due to the increased processing time. If you are using voltage divider, you will be able to define an increment which depends on number of bits. So delta V, the increment, will be 1 over 2 to the power n times total reference voltage. And the V minimum and V maximum defines the minimum and maximum voltage that this digital to analog converter can distinguish. at the end, let us say a couple of words about analog to digital performance specifications. Similar to DAC specification, the resolution of analog digital converter is a measure of the smallest change that can be distinguished in an analog input. Just as in DACs, resolution depends directly on the number of bits, so it is quoted simply as a total number of output bits. The actual value depends on the full-scale range of the input signal. So you can define resolution either full-scale range divided by total number of levels, 2 to the power n, n represents number of bits, or you can quote it as a least significant bit, which is a full-scale range divided with total number of increments, 2 to the power n minus 1. Some analog digital converters have BCD, binary coded decimal outputs. In this case, a resolution is quoted as a number of decimal digits, each requiring 4 bits. In this context, 1/2 digit, which you might hear, is used to refer to a single binary output, only 1 bit, which is typically used as the most significant bit to double the resolution of the decimal digits. For instance, 1 and 1.5 digit converter has 5 bits and covers the range from 00 to 19, 19. So as you can see, by adding this half digit, we are actually adding 1 bit, which can double the range of possible displayed value. Conclusion: the time required to convert a single analog input sample to a digital output is called the conversion time of the analog to digital converter. Conversion time might be quoted as including any other delays in a process of conversion, such as access time. Therefore, the actual number of conversions that can be performed each second is reciprocal to the conversion time. This important specification imposes a limit on the rate at which the analog input can be allowed to change. Again, the Shannon sampling theorem states that the sample data can be used to faithfully reproduce a time-varying signal, provided that the sampling rate is at least twice the frequency of the highest frequency component in the signal. And this will conclude the lecture 4, Analog to Digital Converters, Part 2. Thank you.